All right. Thanks
Yeah.
everyone for being here. I'm Minji Chen. I'm a faculty member at Princeton University, and today it's our pleasure to launch, like Zoom launch, MagNet Challenge 2. I believe many of you have attended MagNet Challenge 1 or has been following the news. So we have a quite successful MagNet Challenge 1, and we developed some new understanding about magnetics, and then we push the state of the art of the community a little bit, and we take a break for 1 year and prepare and think about what we want to do for MagNet Challenge 2, and that's why we are here. So today our intention is to run this as more of a casual discussion because our official launch is at APAC. But we do want to make sure all of you guys around the globe got the news and can start thinking about it and plan your schedule because I know everyone is busy. And also, if you give us feedback, at this point, we can still change our rules. And if you have any recommendation, because we want to run the competition as a open and transparent and inclusive competition. So if you have any ideas for us to make it better, feel free to let us know. And also today, again, our intention is to run this as a casual meeting. So if you have any comments, please raise your hand and we'll enable and promote you as a panelist and you can turn on your camera and mic. So before we start, let me introduce our core team. Like usually, people question who is the people who is running the MagNet Challenge. And I just want to briefly introduce ourselves. So I'm Minji Chen and Professor Charlie Sullivan, who is we sort of started MagNet Challenge together. Charlie, do you want to say a few words to everyone here?
I'm just really pleased to see all the people who are interested in this work and excited by what happened last time. And it seems like there's a lot of potential for even better things this time.
Great. Thank you, Charlie. Shukai.
Hi, everybody. I'm Shukai. You might have seen me in the last MagNet Challenge. This year, we're trying to bring out even more exciting challenge to all of you guys. So get ready, and hopefully it's a very fruitful event.
Great. Hyuje.
Hi, I'm Hyuk-jae, second year graduate student in Princeton. I'm pleased to participate in Prominent Challenge too, and yeah, hopefully have a good result for all of you. Yeah, thanks.
Great. Haran.
Hi everyone, I'm Haran, and great to see you again, some of you, and some new participants, and welcome to this challenge. And then this one gonna be much interesting than the last one, I believe, and I hope you have a great experience.
Great. George, I see your face. I see you are using Alfonso's uh, computer.
Yeah, I passed him the link because he didn't have.
Pass me the link.
Yes. George is the right now you're the community chair for PSMA Magnetics, right? So and Woo's Electronic is sponsoring Magnet Challenge too. Thank you.
Right.
Yeah. Alfonso, do you want to say a few words?
Hi, yeah. Well, welcome to everybody here, and I hope this is as productive as the last one, or even more. And yeah, let's hope that at least we can do some. It would be cool at some point to make a little side competition also for companies.
No, sure. Yeah, I think we're welcoming. Yeah.
Yeah, some healthy competition would be really cool. Also.
Absolutely. So we can't give you awards because it's basically using Wood's Electronics money to pay for Woods. So.
Yeah, no, don't worry about that.
but yeah, you're welcome. So any company and from last year's experience, many people ask like, are there conflict of interest if you are in the organizing committee? Our answer is no. We feel like there's not much conflict of interest for anyone to participate except for Princeton and Dartmouth team. So Princeton and Dartmouth because we have all the data, so we can participate. But other than that, we don't see any conflict of interest because the competition was designed to be transparent and fair. So once we set the rule, it's fair to everyone. Thomas?
Hi, I'm Thomas, and I'm really pleased that we are doing a second edition of that. The first edition, actually, what was really nice is the big diversity of solutions that we got, and it was really nice to see that some people did something completely different than what we thought, and this is really what I'm also hoping for this year, that having a lot of people can bring new ideas for magnetic modeling.
Yeah, so as you'll see this year, the rules are even more open, and I guess the innovation, the space for innovation is even wider this year. So we look forward to see all the creative solutions. Jing Wang, you're muted.
I can hear me all right.
Yes, I can hear you.
Yeah, sorry, my camera is not working. Look forward to the second round. We learned a lot and also had a great chance working together as a team for the first round. So yeah, we'll definitely put same amount of efforts into this one.
Great. Yeah, Jing is I guess you're a faculty at University of Bristol, and they put their results are pretty exciting. They had great results in the MagNet Challenge 1. So welcome back. I believe there are many others here. I can't recognize all your names, so you feel free to raise your hand if you want to speak out. Okay, all right. So without too much delay, then let's move on. Shukai, do you want to go ahead and pull up your screen?
Is everybody able to see my screen? Yeah. Okay. So we can go ahead and start. So, first thing first, I guess in I guess some sort of exciting, enticing news. We are approaching our targeting $60,000 a prize pool. So far, we've garnered donations and contributions from the Pal Society. We have NVIDIA. We're going to give out high-end GPUs to the winning teams. We have Worth Electronics. We're providing $5,000, and ITG Electronics providing another $5K. And so the rest of the three, we are getting very close to them. So we are going to approach our target 60K hopefully before Apex starts. So today is the Zoom launch, is sort of a pre-launch to what the MagNet Challenge 2 is going to be. The official launch is going to be at APEC, which is going to be on March 19th in Atlanta, Georgia. We have a Zoom registration link for you guys who are not able to attend in person. But please, if you're willing to, if you can attend the APEC, please attend this meeting, as we will go over all the other logistics and everything as well to officially kickstart this launch. And we also have a couple of the talks. We have an oral presentation by Hyukjae and me, which is going to talk about the MagNet-X database. What did we do? What data did we collect to sort of provide, to be able to provide it for this MagNet Challenge 2? And we also have a poster presentation on Thursday, which talks about the foundational neural networks that we have developed as an example, which you may see in the future slides, based on the data we have currently collected. So very exciting talks. I hope everybody can attend those if you can. But overall, very exciting APEC this year.
Just one more thing. So we're going to provide a basic tutorial model, just like MagNet Challenge 1. But what we feel is that we're just scratching the surface. What we have developed is just very, very basic. And we are, unlike MagNet Challenge 1, where we sort of know what we're expecting. This year, we have the data. We have some very simple model. But I guess the sky is high. Like there are a lot of possibilities for innovation here, as you'll see.
Right. So the MagNet Challenge 2025, we as the organizing committee, as we just introduced ourselves, there will be 6 of us. And we also have a judge committee who are the senior members of the Pal Society, which where they will be the ones who will judge the final, make the final decisions on the winning teams by the next March. And we also have the liaison committee, as well as the advisory committee, who may provide useful information and help along the way as we go through this whole year, 1 year long competition here. Looking back in MagNet Challenge 1, we've had an extremely successful one where all in all, before MagNet, we were sort of, not really sure how far can we reach in terms of improving the Steinmetz equation, right? But after this 1 year long competition, we've seen so many variety of solutions who really exceeded our expectations here. And we can see that after MagNet Challenge, we have pushed that boundary significantly, right, to a new Pareto front, where many state-of-the-art solutions are popping up and finally become many theses actually to other PhD students, which we think is going to really propel us in terms of improving our steady state Steinmetz solutions, right? Now, building on this momentum, we have decided to launch MagNet Challenge 2, whereas compared to MagNet Challenge 1, we're sort of only improving on the Steinmetz equations, basically a sort of a sequenced scalar modeling where we can improve the core loss modeling of our magnetic materials. MagNet Challenge 2 is looking at differently, where instead of saying, look, how can we improve the Steinmetz equation alone? How do we actually model magnetic material as a material where it may exhibit not only steady state excitations, but also arbitrary excitations, right? And that is something that is missing from the MagNet Challenge 1. And so we've had models that have tried to model the hysteresis of magnetic materials as listed below here, but without good enough data, which we just were able to collect, the overall modeling framework and the society that's able to contribute to this is very limited, right? So if we compare the two MagNet challenges, right, MagNet Challenge 1 is really just to find something that's better than the Steinmetz equation. But MagNet Challenge 2 is increasing, which broaden the entire field up and say, well, instead of just finding something better than Steinmetz, right, what is sort of the best modeling framework for a magnetic material, not only just in steady state, but also any arbitrary excitations, right? How do we model the material as a whole? So with that in mind, we've sort of come up with this foundation model concept for our magnetic materials, where in this foundation model, we hope that to describe the future behavior of the magnetic materials, we need to read some type of that historical excitation to be able to help us predict the future output based on that future input, right? And the entire model should be somewhat of a frequency agnostic nature, as in now we're in a sort of this non-steady state excitation. Instead of steady state, we're doing this arbitrary excitation. So theoretically, your excitation is not going to be a fixed frequency excited waveform. It's going to be arbitrary, meaning that my model should be able to ignore the effect of frequency and just say, well, I can read down on history and predict based on the history and the next few steps or one step input to give me a good reaction of the material for the next time step output. And in addition, we should also have this concept of universal time step, as in when you have your model, right, our data may be in longer or shorter time steps, right? But your model should be able to adapt to shorter time steps or longer time steps and still give very good prediction, right? So it should be a universal time step model here. And then lastly, we have this hypothesis where when you have a transient excitation, hopefully the initial impact of this initial state, right, only has a finite time horizon, as in over time, it will hopefully converge to some type of material steady state condition. So all in all, we wish to have this rigorous mathematical framework here where hopefully we can achieve a very compact and efficient and hopefully explainable as well framework that can converge over time, right, to a material steady state condition, which is not easy to do. And as usual, you can develop a physics-based, data-driven, or hybrid solutions as you wish. And I think this is where most of the teams will have a very diverse way of thinking about how do we approach this problem. So if we do a comparison to the first challenge that we did, right, as in most teams are sort of running around this racetrack and hoping to see who is faster, but having one fixed solution here, we are really opening this up, right? We're opening this up as in we're no longer doing this circular racetrack type of deal. Instead, we are sort of having this point A to point B, and who can find the best route to, as in the best model to describe a material's behavior with the non-periodic or periodic excitations, which is going to be very much more exciting, in my opinion, than MagNet Challenge 1, albeit MagNet Challenge 1 being very useful to our community here. And currently, we do not really have a good method to design magnetics that are operating in transient. And in this case, in transient, we're not talking about completely random transient excitations. Here, we are sort of talking about in-power electronics, for example, for a PFC, a power factor correction circuit here. You may exhibit a random, not so random excitations that are operating in very high frequency with a overall periodic lower frequency excitation from the line, right? And so these type of behaviors are not so arbitrary after all. And these excitations are actually sort of pseudo-periodic, right? Pseudo-steady state. But for these, you're not able to use the data we got from MagNet Challenge 1 and say we can model this type of behavior. And we have many applications in power electronics where such behaviors exist. And so if we have magnetics that are operating under these conditions, then previously we may have imprecise model because we don't have good high quality data. So we may not have a precise model here. That would then cause the designers to create unnecessary design margins, right? Either for thermal or for the saturation and inaccuracy, or either the batch-to-batch variation here. And those will cause us to create a magnetics that is larger than it needs to be, which then also contributes to perhaps if we need unnecessary design margin, then perhaps we also may not be able to choose the right material for it because our understanding of materials are also pretty much so lacking. So this really, on an application front, gives us a motivation for MagNet Challenge 2 to say, well, if we have a good model, can we have that opportunity to reduce the size of our magnetics by hopefully 20 to 50%, and in the end, maybe making every AC to DC adapters 30% smaller. And so that itself is already a huge motivation to what we are about to achieve in this MagNet Challenge 2 here. So then you may ask, well, this is a great idea and this is great for challenge, but how do we collect data that are high quality enough and are good enough for this challenge alone? And creating the algorithm to collect these data is not a trivial idea either, because compared to a steady state excitation, in its name, steady state, which is much easier for us to do, and we can downsample it to have one sequence just for one periodic steady state. Transient excitations are much harder because as you can see here, the way we collect the data is some type of subcycle excitation, and these subcycle excitations are basically within one full periodic steady state. So within one full periodic steady state, you may have, in this case, 6 subcycle excitations, where here each subcycle exhibit different duty ratio step changes. And so you may see that this is not, strictly speaking, a purely arbitrary excitation waveform, which is true. And this is, if we want to achieve a real true transient excitation, you may have to be the job for MagNet Challenge 3. But here, the reason why we're doing this combination of high frequency transient with low frequency steady state is that, one, if we just start, because we're collecting the data in terms of voltage and current, right? And then we're integrating the voltage to get the flux density. If we start from any random point, we may not know the starting point of our B, right? And that is one big issue when we are collecting the data, as in we need to sort of know where the B starts, but with no complete loop, as in no complete steady state, it is hard for us to know. And from a circuit perspective, we have capacitor, DC blocking capacitors in our circuits. So to achieve charge balancing, you also sort of need to create this larger full cycle, steady state cycle. So to create a pseudo steady state excitation here. And this is also applicable to PFC converters, as we saw from the previous slide. And so in this case, when we collect our data, we basically collect give only the duty ratio step changes. And for the frequencies, each one of these sequence is a fixed subcycle frequency. And so all in all, for our entire database for one material, we have about 7 subcycle frequencies, and each one of them having the duty ratio step changes for each of the sequence. So all in all, for 15 materials that we've so far collected, we have over 5,000 sequences like this per material. And we have 3 different temperatures that are included, which is 25 degrees, 50 degrees, and 70 degrees C. And unlike this one, which is only 6 cycles, we have 6 subcycles. For each one of the sequence we actually collected for MagNet Challenge, we have about 100 subcycles for each one of the sequence for all subcycle frequencies. And in this case, we're adopting a fixed sampling frequency for all our data, which I'll introduce in the next slide, and also why we decided to do fixed sampling frequency this time compared to MagNet Challenge 1, where we have a fixed 128 points per sequence there. So because we want to push for the frequency agnostic characteristics for our models, either in machine learning or physics model, we wish to say, well, maybe it's a good idea that we do not include any frequency information as a separate variable that's going to be injected into our model. And so if that's the case, you still need your model to somehow distinguish one frequency from the other. Then for our data, since when we collected our data, each one of the subcycle frequencies are collected with 100 subcycles per sequence. Meaning for 50 kilohertz, you're inherently going to take much longer for 100 subcycles compared to 800 kilohertz. And so that means if we want to have the model to somehow distinguish one frequency from the other, perhaps it is the best that we adopt the same sampling frequency for all of our sequences. So what that indicates is that for a 50 kilohertz sequence, like shown here, you may have 320 steps, right, time steps per subcycle, compared to an 800 kilohertz data where you only have 20 time steps per subcycle. And when we provide you guys the data for training, we essentially are going to provide you 7 sets of the B and H sequences and temperature information for each material, because we have 7 different sets of subcycle frequency data. And as you can see here, the file sizes may vary, because for the 50 kilohertz, in all, for 100 cycles, you may have 32,000 steps. But for something like a 500 kilohertz, you only have 3,200 steps. And so that will be able to distinguish each one of the different frequencies all in all. And for training, as a participant, you may use the data in however way you want. You may divide this long sequence into many small sequences, but the choice is yours. We are just going to provide these raw data to you guys. But for testing, we are hoping, we're still discussing over this, but we're hoping to have the same length for all our sequences when we provide the testing data to test the to validate the to evaluate your models. So what should the outcome look like here? Well, first we will provide 10 training materials to you guys with many pairs of BH, many BH pairs, and also the temperature information. And each of the sequence may look like this BH pair here. And so then we will provide you with the testing data for the 5 new materials. And so then for us testing, we are hoping that the BH pairs are going to take in the memories of the past from time 0 to time 1 of both B of T as well as H sequence. And given the future input of the B sequence from T1 to T2, we are going to evaluate what is the response of the magnetics in terms of the future H sequence from T1 to T2. Now, this past may be very long, as you can see here, to predict a short future, but we can also have a very short past to predict perhaps a longer future. And so this can be a variable, this can be a very different result to based on the models that you have. So we're expecting some type of variables here. But basically, the general concept is using the past B and H pairs and giving the new B input, what is our H output from time 1 to time step 2. So overall, the strategies to win this challenge, as we've seen from the outcome, is that hopefully the student teams are able to provide a model that can be reasonably explainable, and it strikes a good balance between a generality of how well your model can accommodate to various conditions, to your model accuracy, where you can provide a very good prediction of our future for the materials. right? And there are two things that we see as a huge contribution to this field, which one is, well, perhaps we can provide a very good modeling framework, right, to help push the manufacturers to do better. And two, this type of using the history to predict the future can actually be a great implementation tool to be implemented into something like a spice simulator when most of us use transient simulations all the time. And it seems like this can be a really good fit for that. And we also think that because this problem is very challenging, but at the same time, in other fields, there are applications that are much more complex than this one. So we encourage the student teams to also go out there and look for perhaps solutions from computer science community who have perhaps done similar modeling framework for stock markets or for any forecasting, any future forecasting type of solutions are all great to help us to achieve what's here for the MagNet Challenge 2. But also at the same time, we want to make sure that we have a good understanding of it, and maybe we can challenge our existing understanding and perhaps say, well, maybe there's a better way based on what other people have done. Maybe there's a better way specific for MagNet Challenge 2 for magnetics here. So really the winning team structure is a combination of people who are expert in power electronics, data science, software development, and magnetics in general. So hopefully this winning team can have expertise from each one of these categories. And obviously, we're going to provide a very basic tutorial with what we have done so far. And you can find this paper at APEC. But what we have done is also utilizing the past memories of B and H pairs. But instead of providing a future sequence prediction, what we are doing is the very fundamentals next step. We're using the past memory, and given the next time step B, we're predicting what made the H outcome look like. And here we utilized a neural network structure, which here is in LSTM. We feed in both B sequence of the memory, B memory, and H sequence memory, both into the neural network. And in combination with the temperature information and the next time step B, we're able to predict the next K+1 step. And so this is just a very basic way that we've thought of to start with for this type of challenge. So after all, when you're given a long sequence of, for example, here 100 subcycles, hopefully the prediction can be getting very close to be able to characterize the saturation as well as any other nonlinearities that any initial permeability prediction cannot do, which is you can see in this red-orange graph here. So if you were to use initial permeability to, in an ideal case, right, you will see that it actually deviates quite a bit from the actual excitation that may exhibit. It cannot really see the saturation. It cannot really see the nonlinearities. But hopefully our models are able to somehow get to a point where if you predict autoregressively, you can get a relatively good match somewhere between the measurement and perhaps the initial permeability. Now, for all different models, this may vary. And for the challenge that we're providing, perhaps we may not just provide a long memory. We may only provide a short memory. So perhaps the performance may also vary here. But the fundamental idea is that what we are doing here is the absolute scratching the surface, right? We're hoping that teams can use the data and really get out there and think about a variety of solutions. For example, one very notable one is stock market forecasting or weather forecasting, and we've had many papers from the Computer Science Society who have had applications, right, models for such applications here. And for example, in here, you could use Fourier transform and use different models to provide the different frequency information and combine them all together at the end. But there are just many ways to approach this, which we think the teams can really broaden up this, open up this field here and think about innovative solutions to help us achieve the same goal here.
Just one thing to add. So in MagNet Challenge 2, we are still comparing model accuracy and model size. So the basic model that Shukai is going to provide is a big model, and there are huge room for a team to compress the number of parameters. We also haven't looked at cross material model. Like this model, what Shukai showed is like a good result. Apparently looks great, but there are all the corner cases that we didn't test. We also didn't test cross temperature, cross material. How do we transfer knowledge from one material to another material? So I would say there are just a lot of rooms for innovation. Once we release the data, you can take a look at the data, and you can see it's like a wonderland to play in there.
Yes, thank you. So the information flow, right, of MagNet Challenge 2, as in the overall flow of this, is that we will first provide you guys with the large amount of measurement data of BH pairs with the frequency information embedded in there, and also the temperature as a variable. Now the teams will go in there and start evaluating the data complexity and perhaps select what type of model they may want to approach the problem with. Now this can be equation-based methods, or it can be data-driven or hybrid, as we actually saw this in all three of these in our previous MagNet Challenge. Now, at the end, we hope to collect some type of callable MATLAB or Python function, which we will provide a tutorial over, and that for submission. And then we will provide the 5 new materials with a little bit of a test data hidden, only available to us, where we will then evaluate your model performance in terms of the accuracy, the size, and novelty after you guys have provided the final model for us to test it on. And the judge committee will basically judge each model, the model size, the accuracy, and the novelty, as we did for the previous MagNet Challenge. So if you would like to win, which I hope everybody it's willing to, we hope to have a very simple, robust method, really, to accurately predict our magnetic behaviors, but also at the same time, which we sort of want to emphasize, is that we have a lot of training data. And so how do you efficiently use these training data is crucial, because we have limited resources in our data storage, limited resources in terms of our training, if you are using the data-driven method. And so if being able to efficiently use the data is crucial, because not all the information that we provide you is useful, right? And hopefully by the time you get some type of model, you should be able to provide some useful design insights. As we saw perhaps from University of Sydney last year, they actually provided a design tool. And so these are the outcomes we really look for. And finally, to advance our understanding of power electronics, power magnetics, that is obviously going to be the case once we conclude our MagNet Challenge here. So the model performance that we're sort of looking for is similar to MagNet Challenge 1, where we look at a 95 percentile error on the RMS error of our H sequences. And we're also going to look at a core loss as well. And as for the model size, we think that because this is some type of foundation model, so we really are looking for small, simple, foundational type of small size models here. And the novelty, which I think will really shine this year, where I think teams will look for very innovative solutions. And so in terms of model novelty, I think it's going to be very exciting for us to see. And at the end, we're also looking for model generality, where how do you provide, right? How do you extend this developed model to other materials and other scenarios, right? And the final winner will be selected by the judge committee, as shown here. So finally, from the logistics side, for the student team eligibility, we are going to launch this on APEC, and we will also hand out handbooks to people who are interested. But you can also use the QR code provided on the top right here. That will lead you to the GitHub. And in the GitHub, you will find these slides as well as the handbook. And if you would like to sign up, the form is within the handbook itself. And please, you can submit this letter of intent by May 1st to the pelsmagnet@gmail.com email for our coordination with the team here. And so for each team, we're really not setting this rigorously, but we should be somewhere between 2 and 5 student members to qualify for the competition. But we are not rigorous with this requirement here, and it all depends on the letter of intent you submit, and we will coordinate around it. And we can perhaps also host 2 to 3 teams, like we actually did in the last MagNet Challenge. And then lastly, we also you can also invite many prominent researchers from within the field. You can look for yourself, or if you need, we can also pair you up with one from academia or industry as advisors to each one of the teams. And so lastly, for the timeline, once we provide the APEC official launch, we will provide the Q&A session as well as the tutorial sometime between April and May. We will have the letter of intent due on May 1st, and then the 2-page proposal for eligibility, and we will go through them to make sure that everyone is serious about this who are participating, and we will acknowledge the acceptance by July 1st. And then you will have about 6-7 months to work on your model until November 1st. You will submit your preliminary model, and we will provide you with an initial ranking of all the models. And then, but at the same time, we will provide you with the 5 new materials for you to train on. And then you'll provide the last final submission on December 24th, where then we will use our hidden data to evaluate your final model. And the winner will be selected somewhere around March by the next APEC. So that is overall essentially the flow of this year's competition, very similar to logistic-wise to the last year's, but on a problem statement, it's very much harder than MagNet Challenge 1.
So the important dates are April 1st, we're going to release the big amount of data for the 10 material, where you can do whatever you want. You can play with it, you can use it for other purposes. Basically, we'll release our data before April 1st for the 10 materials. And then around November, we will release new data for the new 5 material for fine-tuning your model, and also the testing data for our final evaluation. So I would say between April and November is the research time. Like, you can use the data we provided for doing whatever you want. And then from November to December, that's the testing time, where You will fine-tune your already trained model with the new data for the new material, and generate the prediction results and submit it to us, and we'll evaluate the performance from there. So important date is April 1st and November 1st.
That's right. Lastly, is the award structure. It's very similar to previous years as well. We will have first place, second place for the performance, model performance. We will also have first and second for the novelty. And then the software engineering will garner its own prize. And then we'll have honorable mentions as well. But the structure may change a little bit depending on the award money that we get for this year. But that is roughly something that perhaps you should keep in mind. And on intellectual property, we really encourage open source culture, open source licenses. So if you need to perhaps have IP protection, then perhaps you should take actions before all these comes up at the end. So we really have no restrictions on the intellectual property here. And so that basically concludes what we have today. Here are some extended readings you may be interested in if you have spare time, but that is overall everything we have. If you have questions, please, you can raise your hand and let us know.
Any comments, questions? Charlie, do you have any words, any comments?
No comments. Happy to take questions. Looks like we have one Q&A.
Yes, let me do it. John is here. John, go ahead.
I'm not sure they can.
I think, yeah,
Hi.
he's here.
Yeah. Hello, can you hear me?
Yes.
Yeah, okay, great. Yes, this is Yan Qing from TU Delft. Very nice presentation, and I see a lot of effort has been put behind this. One question is actually about the cause basically you want to predict from the B to H. You also mentioned the saturation of the magnetic components, right? But the saturation is based on the flux density, the B. So why is not from predicting B from H, but the other way around? This is a little bit confusing to me.
I think we can. My quick short answer is yes, we can. I don't know if they are. Charlie, what do you think? I feel it's.
Well, I could comment on the reason that we have it formulated this way, and you know, both could be of interest, but the reason we have it formulated this way is that in a typical power electronic circuit, you are switching between voltage sources or pseudo voltage sources. And so you are applying a voltage which directly results in what B does, minus some voltage drop. And so the causality makes more sense that way, the way they are used in power electronics applications. That's not to say that all applications work that way, but it's just what we see as dominant.
Yeah, I think from competition perspective, it's maybe really indifferent. So like Charlie said, depends on whether you have a voltage-driven magnetic component or current-driven magnetic component. But the way we collect the data, it's more of a voltage-driven system. So we more setting up the voltage and measuring the current versus setting up the current and measuring the voltage. So that's sort of maybe if we try to find a rationale behind it, we go with B to H, but there's no reason you can't. I would say from science perspective, there's no reason you can't also create a model which predict B from.
Yeah, I agree. I would say the effort that you will be put on the modeling will be perhaps the same. Either it's from B to H or H from B. But later, if this is going to be used in real applications, perhaps from H to B will make more sense. That's
And you generally, but the problem, edge, we can measure edge better, and actually that's related to a question in the Q&A. Was B estimated by integrating duty cycle? That's the challenge of magnetic measurement, right? So edge you can directly measure with current, so it has the same unit. But B, we need to integrate V, and once you start to integrate, all of the error accumulates. So we have better understanding of where the real edge is than where the B's are. So then you can argue whether we want to use edge to forecast B or use B to forecast edge. That's like, I guess that's a question.
Yeah, that's a good point. I mean, if H is easier to be measured and B is more difficult, then it will make more sense to predict from H to B.
Yeah, the challenge is that you can't directly, you don't know where there's ground truth of B. That's the challenge. You know where's the ground truth for H, and then B, it really depends on where you start. So yeah, well, it's just challenging. For now, for us, we will just keep it as B to H. But yes, you're right. Both has its value.
Okay, thank you.
Yes, so the question in the Q&A is, was B estimated solely by integrating duty cycles? The answer is yes. We don't have a really good way of directly measuring B in the material. So and that's why we have to create this pseudo periodic excitation so that we always have some kind of zero crossing and DC. There's no DC, there's DC bias in low frequency, but at low frequency, but overall, generally, the B always swing back and forth between positive and negative.
And we could clarify, not just using the nominal duty cycles and the nominal voltage, but using the actual measured voltage on the second winding.
Correct. Yes. Yes, it's not integrating duty cycle, it's integrating voltage to get the B. There's the next question. So the next question in the Q&A is there going to be core loss prediction in a competition, or is it owning about BH values? So we'll do both. So we'll both evaluating the RMS error of the time sequences in B and H, and we will also evaluate the integrated core loss across the many cycles that we're asking for and compare both. So I guess go ahead, Sai Ram.
Yeah, hi, this is Sai Ram from India. So I just have one question. So while you are providing data, are you going to mention about the converter for which this data has been taken up, or it's just kind of some BH data for a given material? So whether you are going to specify the application or the converter for which this BH data is applicable or so.
So Shuga, do you want to take this question?
Are you saying like which application the data is applied to?
Yeah, like
yeah, so I don't think so. I don't think we're going to provide that information because this is not purely a PFC circuit that we collect the data on. This is sort of a T-type exciting the material with a DC blocking cap. And so basically the excitations that we are taking, for example, as you can see here, we have random duty ratio, we're sort of having an arbitrary, uniformly distributed random duty cycle excitations. So this is not really specific to any application like PFC or anything. So what we're collecting data is really here trying to analyze the excitations done on the magnetics rather than the power converters itself.
So we have all the information published about how do we collect the data. So we use the T-type circuits. You can have multiple levels of voltages, and then to excite the core. But in terms of targeting a particular application, we don't have a particular target. We are interested in a general, the applicable model for hopefully any application with with a high frequency excitation and low frequency sort of steady state. That's
so this data corresponds to a varying duty cycle voltage.
sorry.
This data corresponds to a very highly varying duty cycle voltage with various
Correct.
duty.
Yes, basically
So
every cycle the duty ratio
it
change.
it can be applicable for any converter, which is
Correct. Yes. Yes.
okay, thanks.
Yes. Next question. Let me enable. And I'll go ahead and read. The next question in the Q&A is, will the final evaluations also contain the 3 temperatures? And the answer, yes. We'll only do 3. We don't have more. So it will be only the 3 temperatures, but it will all have. So expect temperature as an input to your next. Is it across a wider temperature range? No, we don't have time or effort to cover a wider range, so it'll be only that 3 temperature, 25, 50, and 75. May I ask which website to download and submit the letter of intent? So letter of intent is on GitHub, where Shukai provided a QR code, or you can just simply search MagNet Challenge 2, GitHub. What else? And we have sent the emails to many of the attendees. So if you cannot find it, send an email to us and we'll send it to you for the letter of intent. Next question, maybe Chen, go ahead.
Yes, this is Chen Liu from Aalborg University. In terms of the duty cycle change, I'd like to ask a question. From the paper, it says it changes from 0.2 to 0.8 with the step size 0.1. But from the slide, I can see it change randomly. That means that means not from 0.2 to increase or decrease with step size 0.1.
Right. So here the step change is minimum, right? So you will see that when you change from, let's say, 0.2 to 0.4, 0.2 to 0.3, and 0.3 to 0.2, or 0.2 to 0.4, these are all possible excitations, step changes we are going to provide. And then you will see that if you go from 0.2 to 0.4 and from 0.4 back to 0.2, the excitation response is going to be a little bit different, right? So that's why we try to create as many combinations of different duty cycle step changes as possible, so not restraining to just 0.1 duty ratio step change, right? Because then this really enriches our database. And so as you can see here, from duty ratio 1 to duty ratio 2 to duty ratio 3, we insert a certain randomness to it so that you will never know that whether this is from 0.1 to 0.4 or is it from 0.1 to 0.9, right? So our database includes many of these possibilities. So yeah, to answer your question, it's not a minimum, it's a minimum step change of 0.1, but it's a maximum you can go from 0.1 to 0.9 if you want to, and which we provided here is probably from 0.2 to 0.8. So
it's random, right?
It's random.
It's
yes.
random.
Okay. And for different ferrite materials, the duty cycle changes in the same way for the database, right?
That's right. We adopt so for example, here we have 100 such sequences. Each sequence adopt a random duty cycle changes for 100 subcycles. All these sequences will be applied same across all different materials to ensure that we have some type of uniform database across all of them with the same duty ratio step changes.
Okay, but it's in a symmetric pattern.
Yep. It needs to be because to complete a full steady state cycle, charge balance, you need the D1, D2, D3, but then you need a negative of those to achieve this charge balance here for our circuit from first circuit perspective as well. So yes, the duty ratio is flipped. First 50 cycles and next 50 cycles are flipped.
Okay.
Yeah.
So for
Thank
each
you.
material, you get 100 data, 100 sequences, and each sequence has 100 subcycle. Right, Hugh J? That's the way how we set it up.
And for 100 subcycles, it's only one round. You know what I mean? Or there are several periodic.
No. So 100 subcycles is one huge period.
One huge
that's
period.
it.
Okay.
When we are
Yes.
collecting, we are continuously driving it with 100 subcycle, and we only give you that one cycle, but it's sort of like 100 sequences out of the much longer sequence.
Oh,
Sure.
okay, I see. And for the future test data, and from T1 to T2, may I ask if the final measured result are they the same with the same historic data, training data? You know what I mean? When you do the measurement, we have some past data, and for future measured data, are they keeps the same?
It will be more or less similar, but the duty ratio sequence are different, right? It will be random. Like you probably won't, your model has never seen. It could be a random combination of duty ratios, but
Yes,
it will be similar.
Yes, but what I mean for example, if I do measurement for one time, then I get some merit result, and then I retest. Can we get the same result?
That's related to repeatability of the material, right? From our experience, it's pretty repeatable. So we'll be happy to report how repeatable the models are. But for the purpose of the challenge, we'll assume that the material is repeatable. Otherwise, it's not modelable, right? So if the material itself is not repeating itself, then it makes no sense to build a model.
Yes.
Work on the material.
Okay, thank you.
Great. So next question, is it possible to form a team across multiple universities? And the answer is yes. If so, are there any specific rules to consider? And the rule is no. We'll try to be as open as possible, as inclusive as possible. Go ahead and form your team, and if we see any troubles or concerns, we will let you know. But generally, we don't see any problem if there's a collaboration between different universities. Arun, will the characteristic parameters of the magnetic material be available? For example, the statement constants, permeability size, etc. The answer is no. For the 10 material we offer, we will let you know the name of the material. So you can go to find the data sheet from the manufacturer and do whatever you want. So because characterizing statements constant by itself, as we learned from previous challenges, it's a challenge by itself. Permeability, there are many different ways of defining permeability. So we're not going to do it, but you can extract it from our data if you want for the 10 material. And we'll let you know the size of the core that we collect the data from. But for the 5 material for testing, the answer is no, because we want to keep it confidential. We don't want, we won't let you know which material the 5 testing materials are, because we want to avoid that. Well, there are probably other data available for those material. Then we have to figure out which data is which, and does the data consistent with each other? Does some teams have access to more data than other teams? So we'll keep the name of 5 material as confidential, but for the 10 material, you will know which material they are. Does that answer your question, Arun? If not, feel free to raise your hand again.
Yeah, may I say something in terms of this question?
Go ahead. Yes, sure.
May I ask if the core you are using are standard core? That means can we buy those kind of cores?
Toroidal.
Market.
Yeah, toroids.
Toroid.
we can let you know for the 10 material, we'll be happy to let you know what they are. And even for the 5 material, we can let you the dimension of the core. That's okay.
What do you mean? Can we buy those kind of cores
Yes.
from the market, or it is are they customized by your side?
No, they are available. You can buy it for the 10 material. You can even collect your own data, and if you want to contribute to our database, you're welcome.
Yeah, thank you.
Okay, I think that's pretty much all we have. I don't know if there are other questions. If not, thanks everyone. So this concludes our Zoom launch of our MagNet Challenge 2. We still look forward to see you at APAC. The information will be more or less the same, but we'll hope to see you in person so that we can engage more and then chat more about every details. And at the same time, we are open to change our rule. So if you see a strong need of changing a rule, or if you see a problem, feel free to let us know. We want to run the competition as a open, transparent, and flexible competition. So thanks everyone. Wish you a good day, good evening, and good afternoon. All right. Thanks.
Thank you.
Thanks, everyone.
you.
Thank you. Bye.
Bye.
Bye.